Row versus column-oriented database storages are two styles by which databases use to store their tables on disk. Each have pros and cons. Nothing is perfect. There are use cases for column-oriented. There are use cases for row-oriented databases. In this video, I want to discuss what is a row-oriented database, or also called row store database, because that's the store type. How is it stored on disk, right? I'm going to also describe the column-oriented database, or also known as column store, or another fancy name is columnar database, because yeah, why not? Just let's confuse everybody by inventing new names. So it's all the same thing. It's just how things are stored on disk. We're going to talk about the difference these two. And then finally, we're going to discuss pros and cons of both. How about we jump into it, guys? All right, guys. So let's say we have a beautiful table like this. Okay. It's an employees table. It doesn't only have 8 rows. It has thousands of rows, right? But for simplicity, we only have these. These are the columns. Straightforward. And the first, I want you to pay attention to this. This is the row ID. This is how databases, it's a unique identifier that identifies the row. It's different than the primary key or this ID. It's just something that has, most of the time, most databases have this internal mechanism to identify this row. Okay, and I want you to pay attention to this. So if I'm gonna submit a bunch of queries on this table, I want to do this without any indexes, because indexes will just complicate the manner and by way we think about column versus row oriented. I want to take them out of the equation and think about them just, we don't have any indexes, we're just scanning the table to answer these following questions. So these are the following queries that I'm going to execute on a row database, and then I'm going to execute the same exact queries on column database and see which one does best for each style of how we're going to store these tables, right? The same table, we're going to store it on row, the same table, we're going to store it on column storage, and then we're going to look how these queries perform. So select first name from employees where social security number equals 666, the devil. And then we're going to select star from employee where ID equal 1, very simple, okay? And the final is the select sum. We're just gonna sum all the salaries of the employees for some reason. Yeah. So the first one, row-oriented databases, guys. So for row-oriented databases, tables are stored as rows on disk. And this might sound a little bit confusing when you first read about it. Like, of course, so saying how else are you going to store stuff in the day? You're going to store row by row, right? So if you think of the disk as a blob, huge blob store of just things that contain just bunch of bits and bytes, then the rows are just contiguous, one after the other. So the ID followed by the first name, followed by the second name, then last name, then followed by the social security number, and then comma, and then the second row starts, right? And then so on. Each row obviously has a different size. It could be variable size because I don't know. So like my name is John Smith and someone else named Hussein Muhammad Nasser, right? So that's a longer name, so it's going to occupy more storage on disk, obviously. And thus the rows can vary. But for simplicity, let's think about their fixed size rows. All right. When I want to read a particular row, I go do an operation on disk called IO read. When I read that stuff, the controller, whether this is an SSD drive or a hard disk, reads in blocks. It doesn't read like bit by bit. Bit 0, 1, 0, 1. It doesn't read like that. It reads in blocks. So let's shove 512 bytes at a time. And when you, or I don't know, 1024 bytes at a time. It depends on the block size. This is something called block size. And once you read that, you're going to get not only one row, you could get 1, 2, 3, 4, 5 rows in a given block. So you get, the act of doing one IO can give you 5 rows. And just not all these 5 rows and all their columns, all their values. So whether you want them or not, you're going to get everything. You're going to get all the columns. So think about that. So technically you need more IOs to find the row you're looking for. So imagine you're doing a table sequential scan on the entire table. So if you're looking for employee with social security number 666, you're going to have to do a block IO. You got, I don't know, 7 rows, then search these rows one by one. You're only interested in the social security number, so you're going to only pick that field. Unfortunately, you got all the fields. I'm not saying that's bad. Could be bad, could be good. Depends what you're doing, but that's what you have to work with. So you have to do a lot of IOs to actually get to the row that you're looking for, because you spent a lot of wasteful reads pulling columns that you didn't need, and you don't have a choice, right? So that's just one thing you have to think about with row oriented. Does that mean they're bad? No, they are beautiful. They are elegantly designed because they are so simple. They are just rows, and you can easily think about them. You can easily implement them compared to what we're going to come up next. So let's dive deep into this. So we're going to take our table and then we're going to convert it into a row based on desk. How will this look like? Let's take a look. This is how it's going to look like. So imagine this gray box as a block, right? And for simplicity, I put 2 rows in the same block. Could be 3, could be 4, could be 5. Who knows, right? It depends on the block size. But think about this as a given block. Each gray box takes 1 IO jump to the controller to pull that block. So once you ask for this block, you got everything, son. You got everything, right? So now this is how it's stored. Basically, the row, comma, it's not really comma, it's just literally consequent, right, values, but I just added comma for you guys to understand. The ID, first name, second, last name, SSN, or the salary, birth date, I guess, when this is John, the occupation, and so on. And so you can see that. And this, I added this so it can indicate the second row. It doesn't really exist. It's just an identifier, like, to allow us that, oh, this is actually a second row just started and then a row just ended. And you can see that these are the 2 rows, 2 rows, 2 rows. So let's execute our first query against a row oriented database. I'm looking for the first name for employee where their social security number is 666. The devil. All right. So let's pull it. What do? We ask, hey, because I don't know. I have to start from the top, right? Because I don't know where employee 666 is. It's not like this number, this field has any relation to the row itself. It's just a random value, right? So I have to pull the first block of the table. Does 666 exist in this? Nope. This is 222, and this guy is 111. That's the social security number. So let's pull the second block, right? Nope, it doesn't exist. This is 444333, right? And yeah, it might look sorted, but it doesn't have to be sorted, guys, right? I'm walking through that query with you, right? Again, no index is nothing. Now I'm gonna pull the next block. So I did 3 reads, and then I happen to find that 666. So I found what I'm looking for. Now I want the first name. Guess what? I don't need to do any extra read. Why? Because the first name is right there in the memory now. Because once I pull this block, it's in memory, it's in the RAM. And when I ask for it, I don't have to go back to the disk because, yeah, guess what? I just pulled it, I found it, now I just, this is the first name. And I know because of the position. This position number 2 is the first name. So, boop, pull it. So once I find something, asking for extra columns are really cheap because we already got them, right? Again, guys, you have to think about this. Whatever I'm going to explain to you, there is no bad or good. It depends on your use case, depends on your queries, it depends on your where clauses. And based on that, you pick row versus column based. We're gonna come to that. So that's the first query. Let's do another query. Okay, I guess it's executed immediately. All right, so we're gonna do select star from employee where ID equal 1, right? And since it's ID equal 1, if this is a sequence, the database can do tricks where it can link this sequence with the row ID and says, okay, ID1 is on row 1001, so I know actually where to jump and pull this row, this block, right? It doesn't have to read other things, but it happened to be that the first block is what we're looking for. So yeah, we're lucky, I guess. But even if we don't have this trick where we link the ID to the row ID, we still have to go through each block, and once we find the block we want, guess what? Now I want all the columns. Can I do this? Absolutely. That is so cheap because all the columns are already in memory, assuming they are not vertically partitioned into another location, right? Vertical partitioning, I talked about that many times in my channels and my courses. So vertical partitioning, where we take a column and put it somewhere else, right? This is not the case. Well, everything is in one beautiful block. So I pulled that block, I asked for the ID, I found the ID, and now the user is asking for every field. I always tell people that, hey, select star is bad, guys, stay away from it. But it really depends what you're trying to do. If you have indexes, try to do less of that select star. Select star, we're going to learn that it's the worst thing you can do in a column-oriented database. Select star. In row, you can live without it, I guess. Still, just be aware of that. So that's cheap. That's relatively cheap because I'm going to pull all the rows and if everything in memory. Beautiful. Assume it fits in memory. So could it only be one block? Not necessarily, because a row can span multiple blocks if it's too huge. Let's say that we have some blob here field, and then it's a bad idea to store blobs in line anyway, but let's assume you do. But that means this row can span 7 blocks, for example. So you need to read all the block. Not necessarily. The database are smart. It's going to read the first block, find the ID, and only the rows, the columns you ask for is going to ask for the rest of the block to fetch stuff. Database have been doing this for years. They know what they're doing. But I want to explain how I was doing this stuff. Awesome. So let's do the same thing, but an aggregate. This is called an aggregate function, which is an aggregate is just grouping by something, right? So you work on one or few columns, mainly one or less. How do you work with less than a column? That's just idiot. I'm an idiot. Okay, so you work with few columns, all right? Let's say one in this example. Okay, so select sum salary from employees. Just sum every salary. Let's do this. So we pick the first block. Well, tough luck. I only wanted the salary. Tough luck. I got everything. Again, no indexes here. With indexes, this could be extremely fast, but I'm just telling you what the database does without indexes. So you pull this. Oh, pick the salary. It's 1001 and 1002. So we summed those two. Now let's pull the next block so we get the more rows. Okay, 1,103, 103K, 104K, sum them. And then pull 105, 106, sum them. So guys, every block we pull, we're pulling row IDs, we're pulling first names, we're pulling last names, we're pulling SSN, we're pulling salary, we're pulling that, which we never use, right? So imagine if I only asked for the salaries, and if they were grouped nicely, that would be awesome, wouldn't it? But now, unfortunately, we're asking salary, but we're pulling all the rows. So that's a lot of I/O. So again, this is not just one read. It can appear in this screen here as a one read. If the row is long, you can read 7 blocks. So that's 7 I/Os, right? I mean, yeah, the databases can do a trick where they send one request asynchronously, read multiple blocks, but regardless, you're hitting the disk, which every time you hit the disk is a duck dies, essentially, right? So try to save ducks as much as possible. Save the ducks, guys. Save the ducks. So yeah, reading, and we're summing all of that stuff. That's not so bad, I guess. Yeah, but you read unnecessary information. That means you almost read the entire table, but you used very very small portion of it. That's extremely inefficient. So raw databases doesn't do well this kind of queries if you think about it. It doesn't mean it's slow. Really depends what do you mean by slow. I mean, you've run these kind of queries. The databases do all kind of tricks to be fast, but if you think about the logic, and I'm not saying this is how databases absolutely work. They have all sorts of trick. Again, multi-threading, they send multiple threads. Postgres send multiple threads to read asynchronously. So they do all sorts of trick to do fast. But let's discuss how column-oriented databases work. So with column-oriented databases, if you think about it, tables are stored as columns first in disk. So think about the first name column, the ID column, the last name column. So what they do is they take the first name and they take all possible values, John, Melissa, Rick, Paul, Hussein, everybody, and pull all of these into and save them in disk as consequent values. And then once that table is done and the last value of the first name is done, they start with the second one, right? Last name, and then so on. So you might say, oh, why are we doing this? And we're going to come to that. So a single block IO read to the table fetches multiple columns with all matching rows, right? So it fetches a column. It could be fetched one column or multiple, depends, right? It depends. Like if you have a small table, you can fetch multiple one. If you ask the database to say, hey, give me this, you're gonna get a lot of rows. That's the trick here. So a single column with a lot of rows. Less IOs are required to get more values of a given column, right? Because if you want to get, as we said, the first 100 salaries, that is extremely efficient in column-oriented database because, hey, just go to the place where we know we stored the salary column and just walk through there because you're going to see the values just consequent. We're going to go into the example. And they are great on online analytic processes as we're going to see in the coming slides. All right, so let's take the same exact table and start as columns. Here's how it looks like. Again, the row ID is very critical here. The ID field is this. This is the first name, second, last name. I keep saying second name. Social security number. This is salary, the date of birth, the title, I think, and this is the join date. Look at this. So look at this. I want the ID 1 and this. Which row is this? 1001. ID 2. Which row? 3. 1003. Why? We're gonna see. Look at this. The row ID is duplicated in every column. So just like that, what is the first thing that comes to your mind? Oh, editing is going to be painful. Because if you delete row 1004, you have to poof, 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 poof. You have to go and mark all these stupid columns, right? Or these blocks. Remember, these are blocks, right? So, and for fun, I split some of them and multiple blocks. Doesn't mean they are like, I know this is an integer, for example, or string. I just split them for telling you that, okay, we couldn't store all 4 rows here in one block, so we had to split it in another block, right? So I can show you different kind of examples. Again, take it with a grain of salt. I just want to explain these things to you. So this is one block, 2 blocks, 2 blocks, 2 blocks, 1 block, 1 block, 1 block, 1 block. Okay, got it? Capish? So this is how it works. So they just store all this stuff in columns. So all the ID field, the entire table is here, right? All the possible values. So this is not just one block. It could be hundreds of thousands of blocks if you have a lot of rows. Remember, everything needs to be updated. If you add a new row, you have to update it in all of these logical structures. So that being said, now we know how this works. Let's put it to the test. Select first name from employee where social security number is 666. So now the database will say, wait a second, you're looking for social security number. I don't need to look at any of other logical structures except for the social security, which is this puppy. This is the social security data disk, right? This is how I store. I know this is the location. So in disk, I know where to point my needle and read this stuff. So to search for social security number, I only need to pull this, right? So now I start reading block by block. I read first block, and I got a lot of beautiful values. I got 555, 444, 333, 222, 111. We did not get 666. So, okay, no problem. Let's pull the second block. This is almost like the row base, but now at the column level. Does that make sense? So now we got it. Ooh, we found it. But now I need the first name. What? First name is not here, son. You only got the 66. Now you found that this is actually 1006. That's almost like how indexing works if you think about it. This is how Postgres stores indexes. It's actually, if you think about this as an index, it's almost very similar, right? It just points to the row. Now, 1006. Row 1006, I know this value. I know the row I'm looking for. This is very critical. And I'm asked for the first name. Where's the first name? The first name is right here. This is the first name. So I'm not going to read these blah. I'm only going to jump right here, right? So obviously we found this row, as we said, and then we're going to jump right, not the first block. I'm going to jump to this block. You might say, Hussein, how did you know that it's in this block and you didn't pull this block? Because I know the row number. And the database does all sorts of trick to say, okay, this block has only rows from 1001 to 1004, right? So I'm going to jump to block number 703 because it exactly locate the row I want, right? Because they have all this metadata mumbo jumbo, right? Again, that's back to our question. The 1006 link with the block is all there. They know, and they pull it and they find it. So we had to do one jump, one block read, second block read, jumped back to another block read, and then we got it. So 3. Nah, not so bad, I guess. Let's do select star from employee where ID equal, and let's see how our beautiful column index column storage do. All right. So ID equal 1. Again, I don't have any knowledge with this, so I'm gonna start ID. Where's ID? This is the ID. So I need only to read these structures, right? Let's pull it. Found 1001. It's 1001. So now I have knowledge of the row. I know which block to read, but the user asked me for everything. Okay, let's jump on. Okay, we found that. Let's jump on to the first name. We know which block to read, so this one. Boop. That's one read. Let's jump on another IO. Last name, because they want the last name. They want everything. Read. Oh, found it because I know. I don't need to read this because I only know which block exactly in each column to read to find my value. All right. SSN. Find. Read. Salary. Read. Birthday. Read. Engineer. Oh, I have a bug here. I should have. I didn't stretch it enough. Engineer. Read. And join date. Read. What have we done, guys? This is the worst query. There is so much thrashing happening on disk that this is the worst thing you can do. Column databases just tanks when you do this, especially if you have a lot of columns and you're asking for everything. And if especially if you have like a lot of AND queries or queries here where you had to jump to find the multiple rows, ooh, that will, dude, do that. Dude and do that. I'm talking to both of you. Dude, do that. Do not do this. Select star. Whether row storage, column storage, do not do select star. This is, do you know how many ducks die when you do this kind of queries, guys? You go to the database, you read all these things. Ducks, every IO kills a duck, right? Save the ducks, please, guys. All right, let's do this. Select some salary from employees. Now that we saw how horrible column-oriented databases can be, let's see how great they are. I want to sum all the salaries. Yes, sir. Where's the salary field? There it is. One read. Done. Done. Well, if you live in multiple blocks, you're gonna read the multiple blocks, but done. That's it. That's it. And if you have caching and stuff like that, woo. And by the way, I didn't mention something. If multiple people have the same salary, column-oriented databases do something called compression and aggregate. They actually, if let's say if three people have 100,000 salary calories. Okay, all of them have a lot of calories, right? So they have a lot of salaries, and then you can just have one entry, 100,000 with a comma base, right? So 1003, 1004, 1005, all of them have the same one. So this is even more compact. So this will give me a lot of bang for my buck by just doing one block. Again, sometimes if there's like duplication, ooh, this is the best thing for column-oriented database. They just shove it in the same row because, hey, okay, they're going to do it as an array. We talked about that a little bit in my Postgres 13. Postgres 13, they just started doing this. Index deduplication, I believe they called it. B3 deduplication, Postgres version 13. They start shoving more duplicated values in a single leaf node so they can compress on. So yeah, pros and cons. Is this thing perfect? Nope. Nope. Nothing perfect. It depends on your use case, guys. If you ask me, I still prefer row-based, to be honest, just simplicity of writes and reads. But there are some cases where you need column-based oriented. To summarize, right? Write and reads, you want a simple structure. And we saw how complex column stores are, right? They're very complex. You have to duplicate. You have to show the row IDs everywhere. That can be a little bit messy for writes and slow writes and reads, right? That's why a lot of people use column-based in warehouses and stuff like that, and lakes, data lakes, where things are just almost static. They don't edit. They just do a lot of analytics on a single column. So that's powerful stuff, right? So let's go through these pros and cons in general. So for row-based, it's very optimal for read and writes, right? And then, well, I'm going to say read and write. I'm going to say transactions in general, or online transactional processing, right? They are very great for this because they are very simple in their implementation. So, and if something simple, we can enhance it and make it more and more efficient as we go, right? That's why writes are fast. Reads are almost fast. It depends how your query looks like. We saw some examples, right? Online transaction protocols, processing, right? Transactions are great for row-based because you start a transaction, we know what rows, what blocks to touch. We can write the write ahead log efficiently because we know exactly what we're changing, right? Versus column, this little bit, the structure is all over the place, so we have to do a scatter shot. Compression isn't really as effective though, because think about it, right? I'm not talking about the deduplication. That's something you can do in the index. I'm talking about just the idea of having the values in the row. The row itself is almost distinct, right? It's almost like a hash because it consists of different fields, right? So you cannot really easily compress it, right? The compression algorithms is not gonna find a lot of tweaks to compress because the values are not consequent, right? Compared to the column oriented, where the consequent values are almost the same type and almost the same thing, right? So you're gonna get a lot of chances of duplication. Like, so you're gonna get a lot of people named John, right? So Johns are gonna be squashed together. So compression is not as efficient with rows because you get all these different things that are next to each other and are completely different, so we can't compress as effectively. Aggregation, we saw how poorly the row-based database did with the aggregation. I mean, we had to query the whole table, but we pulled lots of information that we didn't pick. So column-oriented databases were more efficient when it comes to with aggregation, because we fetch only what we need and we work on that. So if you started fetching information or data that are only what you need, then you're gonna start you be very, very efficient in your query, and you'll only fetch the information that you need, right? So obviously you're gonna have a lot, and you're gonna finish faster than row oriented databases. Efficient queries with multi columns, right? So if you're picking multiple columns in a query or working with multiple columns, usually row oriented are better, right? And again, it depends. I'm talking only about the queries itself, right? So you can have a lot of columns if you want to, but if you're only working with a few of them, that's absolutely fine with column-oriented databases. But if you're actually working and touching all these columns, that could be bad, right? With column-oriented databases. With row, we saw it, right? A fetch on the row give us almost all the columns. Again, unless you have vertical partitioning. So with column-based, writes are slower because we have to update all these beautiful structures. Every column has almost a structure on itself. Think of it this way: how is it stored? So I need to know where is it located and touch it, every column, right? Like very similar to indexes if you think about it. They're perfect for online analytical processing. So if you're doing analysis, you're not touching, you're not writing, perfect column-oriented databases. It compresses greatly because all similar sampling are together, so you can the compression algorithms can do magic on these things and compress them. Amazing for aggregation. We saw beep brr, done. Right, that was amazing. I gotta admit. And finally, it's inefficient for queries with multiple columns. If you're asking for a lot of columns, don't do a column. Don't do column-oriented. I know this is a little bit weird. You think that column-oriented databases or column-oriented data stores or columnar will be great if you're asking for a lot of columns. Nope, they are the worst with this stuff. I know, guys, Postgres, MySQL, other databases, most of them are row-based storage. However, SAP HANA and others have Oracle, I believe. Most databases by default go with row-based storage. However, if you think about it, they have database storage engine, and we talked about database storage in my database course and in my YouTube channel as well. I talked about that. How a database engine, you can swizzle this database engine for a given table. So every table, you can pick a table and you store this table as column store, and you can pick another table and store it as row store. You can swizzle the database engine, right? Based on that, you can just change your database engine for every table based on the needs. If you have a table that only get queried, make it column, for example, right? If you're doing a lot of analytics on it, make it a column, right? If you're doing a lot of writes, probably you want to make it a row store, right? And think about all of this stuff. Like, you cannot, for example, join a row-based store table with a column-based table, right? That's just bad. I mean, some databases support it, but give them a break, guys. Give them a break, because that will be really disastrous. I can't even imagine what the database will do. It was gonna freak out, I guess. All right, guys, that's it for me today. What do you think about these two puppies? Let me know in the comment section below. I'm gonna see you in the next one. You guys stay awesome. Goodbye.